In this lesson, we'll continue with memory management and look at the concept of segmentation. We're also going to look at how paging, which we discussed in the previous lesson, can support the creation and operation of virtual memory. Now, if you remember that paging was used by the operating system to create fixed size memory blocks, segmentation is another technique which is used to optimize memory management, but in this case, we use variable or changing memory blocks. So the difference between paging and segmentation is one uses fixed size blocks and the other uses variable size blocks. Otherwise, they're more or less the same. Now, as usual, we'll begin by looking at some key terms that are associated with both segmentation and virtual memory. So do pause the video and jot these terms down. Now, segment memory is basically variable size memory blocks. We just talked about that. So the logical memory is split into variable size blocks instead of fixed size blocks. Segment number is the index number of a segment, just like a page number. And the segment map table works exactly like a page map table, and it contains the segment number, the segment size, the corresponding memory location in physical memory, and it maps the logical memory segments to physical memory. In addition, we have virtual memory, which is a type of paging that gives the illusion of unlimited memory being available. Now, segmentation is not used for virtual memory, and we'll talk about that. Swap space is a space on your hard disk drive or SSD, which is used in virtual memory. In-demand paging is a form of swapping where pages of data are only copied from the hard disk drive or SSD into RAM when they're actually needed. Otherwise, you keep them in your swap space. Disk thrashing is a problem resulting from the use of virtual memory. You might end up excessively swapping pages between RAM and your swap space, and that can lead to something called a thrash point, where you end up spending more time swapping pages rather than doing anything else like processing, and that can lead to system stalls or even crashes. So hopefully you got those key terms down. Let's start by looking at segmentation. And in segmentation, logical address space is broken into variable size memory blocks or partitions, which are called segments. So instead of being fixed like paging, we've now got changing blocks depending on the need of the process or the program. Now, each segment has a name and size, and for execution to take place, segments from logical memory are loaded into physical memory just like paging. Otherwise, everything is the same. The address is specified by the user, which contains the segment name and the offset value. Now, this value decides how big the segment is going to be, so the variable nature of the segment depends on the offset value. The segments are numbered, and rather than using a name, this segment number is used as the index in the segment map table, just like a page number is used as an index in a page map table. The offset value decides the size of the segment, and you work that out by simply looking at the segment number and adding the offset value. So if the offset value was calculated to be 55 and the segment number was 5, the address would be 60. Now, just like a page map table, a segment map table contains all the usual information that's needed: segment number, segment size, the start address, and physical memory. The only difference here is that in a page map table, you can map blocks one to one because they're equal sized. Segments are variable. So what basically happens is you have your segment number, then you have the size of the segment, which varies depending on the processes, and then you have the memory start address. Now, if you look at the example, segment number 1 has a variable size of 400 and it starts at 1000. So it will continue on to 1300, 1000, 1100, 200, and 300. Therefore, the next segment, which has a size of 700, can only start at 1400 instead of, let's just say, 1100. Physical memory ends up becoming contiguous rather than fragmented. And that's the benefit of using segmentation in a way. Otherwise, it works exactly like paging. It's just a different way of organizing and mapping memory. Now, summarizing paging and segmentation will allow you to see the differences and in a way see how similar they are as well. In paging, a page is a fixed size block of memory. Segmentation includes a variable size block of memory. And since in paging this block size is fixed, it's possible that blocks may not be fully used. You might end up having internal fragmentation. And because memory blocks are variable, this reduces the risk of internal fragmentation, but increases the risk of external fragmentation. What does that mean? That means that the RAM in segmentation doesn't get fragmented as much as the logical one. Whereas in paging, the logical one tends not to be as fragmented but the RAM part, or the physical memory, gets more fragmented. Now in paging, the user provides a single value. This means that the hardware decides the actual page size, whereas in segmentation, the user normally supplies the address in two values, the segment number and the segment size, which basically is related to the offset value. Now the page table will map logical addresses to physical addresses, which is exactly the same way in segmentation. It uses a segmentation map table, which maps logical addresses to physical addresses. The process of paging is essentially invisible to the user because they are not involved in deciding the page size. It just works behind the scenes. Whereas in segmentation, it's actually a visible process because the user needs to define the offset value. Now, procedures and any associated data cannot be separated when using paging because blocks are fixed size. So you might end up with, let's just say, 3 instructions and 2 sets of data all together. Whereas in segmentation, we can separate the instructions and data into different segments. Now, paging consists of static linking and dynamic loading, whereas segmentation consists of dynamic linking and dynamic loading. Static links basically means that the links are fixed between the different block sizes, whereas segmentation supports dynamic linking. That means that they change because the sizes are variable. Dynamic loading basically means that both support in-demand swapping of data. So when a process is in the ready state, it's only then that their data is loaded into the main memory. Otherwise, it stays in the virtual swap space. And finally, pages are usually smaller than segments due to their fixed nature. One of the biggest problems encountered with memory management is situations in which processes run out of RAM. RAM is always available in fixed amounts. You might have 4, 8, 16, or even 32 GB of RAM, perhaps even more. But whatever amount of RAM you have, sooner or later you're going to run out of it because processes will use that RAM for their own purposes. Now, if the amount of available RAM is exceeded due to multiple processes running, it is possible to corrupt the data which is used by some of the programs which are currently being run. Now, this type of situation can be solved by separately mapping each program's memory space to RAM and also utilizing secondary storage if we need more memory. Essentially, the RAM is the physical memory, and the virtual memory that we're going to end up creating is the RAM plus the swap space on the hard drive or SSD. So we simply say, well, okay, we've got 16 GB of RAM, and if we need more, we're going to allocate another 32 GB of storage space to act like the RAM. That's your virtual memory, the RAM plus that hard drive or SSD disk space. Now, a key point to remember is that virtual memory is normally implemented using on-demand paging. We can use segmentation, however, it's a bit more difficult to manage. Now think about it, when you have variable size blocks, that's going to be quite challenging to manipulate in a fixed amount of memory. It might be more easier for us to manage equal size blocks. The images on screen illustrate this much more effectively. You've got 5 instructions in the program and RAM only has 4 1 GIB spaces. So the last one can't fit in and that can lead to a system crash. However, if we had virtual memory in place, the first 4 will go into RAM and the 5th one will go into the hard disk space. Now, virtual memory offers a lot of benefits, and these include that programs can be larger than the actual physical memory and still be executed. It leads to a more efficient multi-programming model with less input-output loading and less swapping of programs in and out of the memory. There is no need to waste memory with data that is not being used. That data can be moved into the swap space. It eliminates external fragmentation and reduces internal fragmentation. External fragmentation is the one that you have on your swap space, and internal fragmentation is the one in memory. It removes the need to buy and install more expensive RAM memory. We can just substitute cheaper SSD or HDD storage space, and we can use that in the short term. Of course, virtual memory also has drawbacks, and the main drawback is that if you're using the hard disk drive or the SSD space, then that's going to mean you have less space on your hard disk drive or your SSD to store your programs. And as the main memory fills, more and more data will be needed to be swapped in and out of this virtual memory as well. So that means that you might end up spending more time loading and unloading pages than doing actual processing. And this high rate of hard disk read-write head movements is known as disk thrashing. You're thrashing the disk by just reading things into memory and writing things back from memory to your hard disk drive swap space. Now, a point can be reached when the execution of a process actually comes to a halt, since the system is so busy paging in and out of memory, so swapping pages and frames, and this is known as the thrash point. So when you reach this thrash point, everything stops. You might end up with a crash. Now, another consequence of this is that if you are using a hard disk drive, then these constant head movements can lead to premature failure of a hard disk drive as well, because physical devices or physical components are often limited to the amount of times they can move before failure, and that can cause a huge problem. Now, thrashing can be reduced by installing more RAM, or you can reduce the number of programs running at a time, or you can reduce the size of the swap file as well. All of these will allow you to make sure you don't hit that thrash point. So how do programs or processes access data when using virtual memory? Well, the process goes something like this. The program executes the load process with a virtual address. The computer translates this address to a physical address in RAM, and the operating system probably knows that these addresses are in the RAM and these are on the swap space, but the computer thinks everything is in this extended virtual memory or extended RAM. If the physical address is not in the actual physical RAM, the operating system loads it up from there. So the computer kind of gets fooled into thinking this entire virtual memory is the actual RAM or physical memory. The computer then reads this extended virtual RAM, and then it can read and write data to it. Okay, we're going to stop here for today. Hopefully you know how paging works and how segmentation works and what the difference is between paging and segmentation. You should also be able to explain the benefits and drawbacks of virtual memory. In the next lesson, we're going to move on to page replacement algorithms to see how these pages are replaced between the swap space and the RAM. As usual, if you do have any questions, get back to me. Otherwise, I'll see you in the next one.